Hey everyone, welcome to today's topic, and this one I hope is going to change how you think about every poll, survey, and research study that you encounter. So we are diving into sampling, um, and I promise by the end of this, you'll be that person who questions every headline that starts with "studies show." So picture this. You want to know what all college students think about mental health resources on campus. Sounds simple, right? Except there are over 20 million college students in the United States. So good luck getting a hold of all of them. It's just not going to be possible. Even if you had unlimited time and money, students are graduating, new ones are enrolling, some are studying abroad. Your population is constantly changing, and that's why we need sampling. So when conducting any research study, we're always juggling two things: our population of interest, everyone we would love to study, and our sample, the people that we can actually reach. And um, we also need to think about something called our sampling frame, okay? Sampling frame, the actual list or method we use to access the population. If you want to study college students, your sampling frame might be student enrollment records. But, what about part-time students? What about online students? What about students taking a gap semester? Your sampling frame might miss people you actually want to include. It's like trying to sample all young adults, but only using Instagram users. You're missing people who aren't on social media. So the beauty of sampling lies in something that it's almost magical in a way. When we pull samples from populations, they often represent the larger group in meaningful ways. So think about taste testing soup. You don't need to drink the whole pot to know if it needs salt. You get one spoonful properly mixed, and it tells you about the entire batch. So here's the fundamental goal. We want to make inferences from small groups back to larger groups. It's like reverse engineering. We study the part to understand the whole. So this process forms what we call the statistical model. You sample, you analyze, you infer back to the population. That's the statistical model. Consider some real-world examples, okay? So Netflix studies viewing patterns from samples of users to recommend shows to millions of users. You have political polls that survey like 1,000 people to predict how 150 million voters will behave. Medical researchers test drugs on hundreds of people to make recommendations for millions of people. So we do this because studying entire populations is usually impossible, impractical, or the worst, expensive. So imagine if pharmaceutical companies had to test new medications on every single person before approval, right? We would never get new treatments. So now let's talk about our gold standard, random sampling. This means that every person in your population has an equal shot at being selected. It's like putting everyone's name in a giant hat and then, drawing blindly from it. So in practice, we usually let computers do the heavy lifting. We've got software like Excel, SPSS, online random number generators that can do the selection for us. If I wanted to randomly sample from our class, for instance, I might assign each of you a number, let a computer pick, no favoritism, no bias, it's just pure chance. But here's a reality check. So true random sampling is harder than it sounds. Even if I randomly select 5 of you for a study, what if one person has a job interview that day? What if another just doesn't feel like participating? Suddenly my random sample becomes whoever's able and willing. And this happens constantly in real research. So imagine randomly calling 100 people in your city for a survey. How many do you think will actually answer? How many would hang up when they realize it's a researcher? They might think you're a telemarketer. You might end up with responses from 30 people. But are those 30 representative of everyone you called? So despite these challenges, randomness remains our gold standard because it gives us the best shot at representation. But, and this is crucial, randomness helps achieve representation but doesn't guarantee it. It's like shuffling a deck of cards. Just because you shuffle doesn't mean you'll get a perfectly distributed hand. So before we explore different methods, think of actually, let me just stay up here for now. Think of sampling like dating apps, okay? Some methods give everyone an equal chance of matching, probability sampling, while others rely on who's most likely to swipe right, which would be non-probability sampling. So probability sampling methods give every population member a known non-zero chance of selection. These include random, systematic, stratified, and cluster sampling. So with these methods, we can actually calculate our margin of error and make really solid statistical inferences. Okay. Non-probability sampling methods don't give everyone that equal chance. These include convenient snowball, purposive, and voluntary response sampling. We're going to talk about all of these, okay? So they're often more practical, but they limit how confidently we can generalize our findings. So if you think of it this way, probability sampling is like a scientific experiment, while non-probability sampling is more like educated detective work. So systematic sampling. Here's a method that's often more practical than pure randomness, systematic sampling. So instead of randomly selecting each person, you select every nth from a list, okay? So I guess I shouldn't be on that. This is still kind of like random sampling. It's every nth method, systematic sampling. So instead of randomly selecting each person, you select like every 100th person or every 10th person from a list. So this is like sampling every 20th customer who walks into a store, or every 15th fan who comes into the baseball game to be searched. It's systematic, predictable. It's often easier to implement than a true random sampling. But the catch is, if there's a hidden pattern in your list that matches your selection interval, you could accidentally introduce bias. So imagine sampling every 7th person from a list organized by the days of the week. You might only get people whose name start with certain letters, or people with a certain job, or something like that. Okay. So sometimes there's a pattern and we don't realize it's there. So that's a type of random sampling. It's not exactly random, but it's kind of random. All right, stratified random sampling. So this is about ensuring that everyone's voice gets heard. Okay, sometimes random sampling just doesn't cut it. So what if you're studying like social media usage, but your random sample gives you 90% of people over the age of 65? That might not represent the full picture. So, this is where stratified random sampling comes in. Think of it as creating fair teams for a basketball game. You don't just randomly grab people. You make sure that each team has a mix of heights, skills, experience. If you want to study like campus dining satisfaction, but different class years might have very different experiences. Freshmen are stuck with meal plans. Seniors often cook for themselves, like if this is a college with a dorm. A random sample might give you mostly juniors and seniors. With stratified sampling, you'd create separate groups, what we call strata, for each class year, and you sample equally from each of the stratas, each of the groups. That way you hear everybody's voice, okay? Here's a local example, okay? If you're studying ethnic diversity experiences in Southern California, some groups are much larger than others. Stratified sampling would let you ensure that smaller communities like Pacific Islander students, for instance, or Native American students have equal representation alongside larger groups, giving everyone a voice in your research. So you could do this with majors across campus. Engineering majors might have different stress levels than art majors, and there's more of one than another. So stratified sampling ensures that you hear from both, even if one group is much larger. So, non-probability sampling, okay, non-random sampling. So sometimes that gold standard random sampling just isn't feasible. What if you're studying people with rare psychological conditions? What if your budget is basically zero? This is when you use non-probability sampling. It's messier, but it's often what really gets the research done, okay? Convenient sampling is the whoever shows up method. It's exactly what it sounds like. You take whoever's available, whoever's easily available. It's like surveying people at the mall because that's where you happen to be. And that's what we're going to be doing in our class. We'll send out a survey link and whoever responds, responds. There's no randomness, no complex selection criteria, just whoever's willing to click and participate. It's not perfect, but it's practical. And sometimes practical trumps perfect. The snowball sampling method is like the friend of a friend method. It's like how you'd plan a party for a very specific group. You start with one person from that community and they help you find others. So this method really shines when you're trying to reach hard to reach populations, right? So imagine researching people like in recovery from addiction. Many are skeptical of researchers. They don't like participating in research because they're worried that it's actually like a treatment program or rehabilitation program in disguise. But if you earn the trust of one participant, they might introduce you to others in the support group. One connection leads to another, and your sample grows like a snowball rolling downhill. So this works great for studying autism spectrum communities, places where trust and rapport are essential, or where it's hard to find people. Any group that might be wary of outside researchers, any rare group, any hidden group, snowball sampling is going to be great for. Voluntary response sampling, the pick me method. Voluntary response sampling happens when people choose themselves for your study. So think about online surveys, participate in research flyers in coffee shops, or people who call radio shows to share their opinions. When the people who volunteer for these things, they often have reasons to do it. Okay, so like for instance, I volunteer for neuroscience studies because I think brain research is really interesting, but that makes me different from somebody who would never volunteer. I'm probably more interested in science. I have more free time. I enjoy being a research participant. So this creates volunteer bias. People who self-select might systematically be different from those who don't volunteer. The upside is that voluntary response often gives you the biggest samples because you can cast a wide net and, easily get people to participate. So response rates are something that keeps researchers up at night. Even with perfect sampling, what percentage of selected people are actually going to participate? So imagine you perfectly randomly sample 1,000 college students for a stress survey, but only 300 respond. And now you have to ask, are stress students more likely to ignore surveys because they're too busy? Are less stress students more likely to participate because they have time? And this creates non-response bias. So your final sample might not represent your intended population, even though your selection method was perfect. So response rates for many surveys have been dropping for the past number of years. Something that's really interesting. People are busy, suspicious of scams, survey fatigued. Researchers have to get creative with incentives, follow-ups, make participation as easy as possible. Purposive sampling. We need that specific person method. So sometimes you need very specific people for specific reasons. Purposive sampling is like casting for a movie. You're not looking for random people. You're looking for people who fit exact criteria. And this is huge in case studies. Researchers purposefully selected, you might remember the story of Phineas Gage, the railroad spike through the head guy, because his brain injury was super rare and it offered unique insights into how the frontal lobe functioned. They didn't randomly stumble on him. He didn't volunteer. They specifically studied him because of what happened to him. Okay, or like Kim Peek, the inspiration for Rain Man, if you've ever seen that movie. Watch it if you haven't, it's great. Tom Cruise movie. Researchers didn't randomly find someone with extraordinary memory. They purposefully studied him because his abilities were so unusual. So purposive sampling is great for when you only have a tiny population. There's not many people who are like that. You couldn't find 30 people who've had a railroad spike, shot through their head with dynamite. Like, that's just not going to happen. Let's talk about the ways sampling can go wrong, because understanding the pitfalls, makes you a smarter consumer of research and a better researcher. So you have selection bias. It's like a bouncer at a club who only lets in certain types of people. Your sampling method systematically excludes or overrepresents certain groups, okay, on accident. So you accidentally exclude or overrepresent certain groups. If you're conducting phone surveys, you're missing people who don't answer unknown numbers, probably younger people. You're missing people without landlines. Okay, you're biased in your selection. Volunteer bias we've covered. Those are people who choose to participate, and they're different from those who don't choose. Think about like who would volunteer for a study about sex. Somebody who's much more comfortable with sex, probably somebody who has a lot of sexual experience, so volunteer bias. Non-response bias we talked about happens in a well-designed studies, as well as poor studies, when the people who don't participate are different from those who do. So political polls often struggle with this. Are Trump supporters less likely to participate in polls? Are liberal voters more likely to hang up on pollsters? These differences can skew results even with random sampling. Okay, sampling error and margin of error. So this is the math behind the headlines. So when you see poll results saying like Biden leads by 5% with a margin of error of plus or minus 3%, that plus or minus 3% comes directly from sampling theory. So sampling error is the difference between what your sample shows and what the true population value actually is. It's not a mistake. It's just math acknowledging that samples aren't perfect, that there's an error. So the margin of error tells you the range where the real answer probably falls. So if a poll says 52% of people support something with a plus or minus 3% margin of error, the true percentage is probably between 49% and 55%. As add or subtract 3% to that 52. So here's a visual for you. So imagine the population as a large box and your sample is a circle inside of it. Okay, so a small sample like the one on the left is a small circle that leaves lots of room for error because you've only sampled a small part of the population. A large sample, the big circle on the right, there's less room for error because you've sampled so many more people in the population. But even huge samples have some error because you're still not studying everyone. Why don't we use massive samples? Why don't we study everyone? Just money, time, practicality. It's just not always possible. Plus, there's something that we call a magic number in statistic, which is an N equals 30. Okay, with 30 representative participants, 30 people in your study, you can make pretty solid inferences. That's a small amount of people, but you'd be surprised you actually can make inferences from only about 30 people. More is usually better. But you hit diminishing returns. So going from 30 to 60 people helps a lot. Going from 3,000 to 6,000 people helps much less. Okay. So if we bring this full circle to our class research, we're going to collect our own data using convenience sampling. Whoever wants to participate, in my classes, this class as well as others that I'm going to send it to. So this means, that we need to look for interesting patterns, explore the relationship between variables, generate hypotheses for future research. These are all things that we can do. But what we can't do is we can't make broad generalizations to all college students. We can't calculate the precise population parameters, and we can't claim our findings apply beyond our sample. Okay, or we have to claim that with very strong limitations. Okay. What we can actually generalize, generalization works best when you use probability sampling methods, random, systematic, stratified, cluster, instead of non-probability. If you have good high response rates, like 70% plus is considered good these days. If your sample represents your target population on key characteristics, right? So let's say your target population is, Japanese Americans. If nobody in your sample is Japanese American, then you can't make a very good generalization. So your sample needs to represent your target population on the key characteristics. So if you're talking about middle class people, you need to be sampling middle class people. And then of course your sample size needs to be adequate in order to generalize. So remember the magic N equals 30. So with our convenient sample, we need to be humble about our conclusions. Okay, our findings might reveal patterns worth investigating further, but we can't make the same statistical claims we could if we were using probability samples instead of non-probability. So the bottom line is every research method has trade-offs. Random sampling is theoretically ideal, but practically challenging. So convenient sampling is easy, but limited in generalizability. Stratified sampling helps to ensure representation, but it also requires more planning and may not be quite as generalizable because you're over-representing certain groups. So the key is being honest about your limitations and matching your methods to your goals. Netflix doesn't need random sampling to recommend shows. They can use their existing user data. Political pollsters do need random sampling to predict elections accurately. So as you go forward, just think critically about every study you encounter. How did they select participants? Who might be missing from your sample? Can their conclusions really be generalized as broadly as they claim? Understanding sampling makes you a more informed consumer of research and a better researcher yourself. So, plus you'll never look at a 9 out of 10 dentists recommend claim the same way again. Okay, that's a sampling in a nutshell. Now you are equipped to navigate, the world of research with a more critical eye. So yeah, that ends our lecture on sampling. I will see you next time when we'll build on these concepts.